The format also that I'm thinking is that I will explain everything, and please interrupt me. So don't wait until the end to ask questions. Try to ask questions related to what I'm discussing, but it's also fine if you have a random question. We are here today, 4 of us, Borja, Niels, Andre, and me, I'm Ismael. Depending on the question, I might redirect to some other guy to answer it. The outline, so what we are thinking to discuss today is to touch on a couple of topics on, let's say, more not theoretical, but the architecture of the code. On this, the interfaces and the threading, I think that are critical parts to understand how the code works. We will also discuss very quickly CI/CD, and then we will do a quick demo on how to run a very simple setup here that we have today with a Foxconn RU, a few handsets, and the G0B running in this PC. I will also very quickly explain how to build and install the software, because most of you already know that, a little bit on configuration. And then at the end, there is a section on discussing typical things that can go wrong, that maybe you're not achieving the best performance or the phone is not connecting. And I will explain like a few tricks, what you should expect and what can you do to fix it. So you all know a lot of this, so I will go quickly through this. You know that it's entirely developed by SRS. It has very minimal dependencies, portable across different CPUs. Very important, the last one, this is a design goal for us. It has been since SRSLT, and it still is. We aim at writing the code in a way that it's easy to trace from the specs, easy to understand. So if at any point we fail to deliver that, please let us know, and we will try to correct it. The features we discussed yesterday, but we are doing a full rate now in 4x4 MIMO. The LDPC and the Polar are optimized for ARM and also x86. There are still a few bits that are missing. There are some formats of PSSH that are not supported. The sampling reference signals still are not supported either in the uplink. In terms of integrations with third parties, we have integrated with a number of RUs. Here we have the Foxconn, but we have also integrated with Benetel and Picocom. The cores, typically it's very easy to integrate. We have integrated with these ones. And rigs is something that we are starting, and we have integrated with FlexRig and NORAN-SC. Hardware acceleration, we support both inline Fappy and Lucasite BBDEF. So it all started here 2 years ago. We decided to focus on the ORAN architecture, and following our philosophy of making things clear, making things easy to understand, easy to extend, we wanted to start the software architecture from a clean slate approach. You all have seen that all the code that we had in 5G, we essentially throw that away, and we started from zero. The idea was to really make a lot of effort on implementing or supporting the ORAN interfaces natively from the beginning, and the reusability of components, the modularity, also very, very well defined. In ORAN, there are many interfaces. The most important for us are, or that have determined the design a lot, are the 7.2 and the F1 and E1, because that forces the code structure to be divided in obviously these blocks: the CUCP, the CUUP, the DU high, and the DU low. The Fappy is not ORAN, but it's an interface that we like a lot. We like a lot because I think that it's relatively well designed. We always struggled a lot before deciding to implement Fappy on how to design an L2 and an L1 interface that is clear to the reader, and that anyone can come and replace the file with another file, or that can understand that messaging. And Fappy really does a good job on defining that. As a bonus, it also allows us to easily support inline acceleration. But I will touch on that later, because I believe that it's very critical to understand Fappy for many of the extensions or customizations or modifications that some of you want to do with the code. In the software architecture, the main design goals were these ones: scalability and performance. I think that are very related. I see it as the ability to run efficiently in a dual core tiny processor, or in a 80-core super big CPU. It's funny because sometimes the number of cores, sometimes when you have many cores, the problem is more difficult, because every core is much smaller. In quad cores, in i7 or i9 quad cores, the CPU clock is very high, and they can do a lot of tasks, and you don't need to parallelize a lot. So scalability and be able to scale in a performant way was key. Disaggregation is also very important. We saw before that we have this O-RAN architecture that, yeah, you can disaggregate everything, but there are some cases where you want to run everything in the same platform. The small cell is a typical case. In a small cell, you would have inline, typically you would have an accelerator, you would have a tiny processor that is running the DU and the CU, everything collocated. So we want to write a software that can easily instantiate into a distributed or disaggregated O-RAN deployment, or in a small cell running inline acceleration. So we have to be able to run, to use the Fappy or not, to use F1 or not, in an efficient way. Clean interfaces, that's a critical design to allow the community, so to allow you guys to be able to replace blocks and improve them, or add your customizations. And portability across platforms is also a key design goal. To achieve that, we did a hierarchical and modular approach. This is something that we already did before, but now we defined even more strongly. And you have also seen that we moved from a mix of C++ and C code into a pure C++. We also adopted design patterns, which is a great tool to solve complex problems in an abstracted way. We decouple a lot the interface from the implementation. We use RAI always to keep the scope of the objects that we initialize. And we also use hardware abstraction. The code, you're already probably familiar with this, but it's organized in these 4 main folders that follows this hierarchical approach. In the include folder, you will only see the headers, essentially the definitions or the declarations of the interfaces. All the implementations of these interfaces will go into the lib folder. Then you have the test folder where you have unit tests, but also benchmarks. Today, someone was asking me about benchmarks. You will find them there. And then you have the apps folder. For us, the app is the G0B or the CU. I don't know if it's easier to read like this, or you prefer before. Before, no? It's okay? Yeah. So for us, an app is the CU or the DU or the full G0B. So going back to this diagram, if you want to instantiate a small cell collocated G0B, that's one instance. So that's the G0B. you will find that G0B binary in that app folder. In the future, in the next release that we will support a CU and DU split, you will find 3 binaries, one for the CU-UP, one for the CU-CP, and one for the DU. And you will think, okay, but how do you do that? So you will be rewriting a lot of the code. The answer is that in this apps folder, there are no implementations of anything. And the binary of the G0B will only put together these pieces, okay? But will not re-implement any of the procedures. This is another example of the interface or the decouple between the interface and the implementation. We have an interface like the PSCH decoder that will have a method that says new data arrives, process it. We can have, in this case, we can have 2 implementations. One that would use the ACC 100 in look-aside mode, and one that would use a software implementation. This software implementation will use 2 blocks, the rate dematcher and the LDPC decoder. Again, these are 2 interfaces. The LDPC decoder will have a method that says decode, and at the same time, the software implementation of this LDPC decoder will use these other interfaces. So say that now, and by the way, all the dependencies are injected in factories, which are created at runtime. So say that now you come here and you want to implement your own PSCH decoder. You have different options. If you want to implement everything, the rate dematcher, the decoder, the equalization, everything, you come here and you just inherit from this interface and implement your own PSCH decoder, and you call it my implementation. Say that you are happy with the whole DSP chain of the PSCH decoder, and you just have a better way of implementing the neon, let's say the neon implementation of the LDPC decoder. Then you just need to come and replace this block. But the rest, you don't need to change anything, and everything will work and compile and run correctly. The Fappy, I said before that I think that it is very important, and I think that it also helps a lot to illustrate this. So what this decoupling between interfaces and the implementation allows to do. Fappy very well defines the messages that go between the MAC and the PHY. And this separation, so the Fappy in itself is an adaptation layer between the MAC and the PHY. What this enables is that from the point of view of the MAC, it does not depend on the PHY. The MAC uses its own data types and communicates with the Fappy using these data types. The PHY uses its own data types and communicates with the Fappy using these data types, but they are completely decoupled. You won't see an include in the MAC that depends on the PHY and vice versa. That is very useful because allows, say that you are very brave and you want to implement your own PHY. No problem. You can completely remove all the PHY files and replace with your own PHY, and everything will still compile and everything work. As long as the only thing that you need to comply is with the interface with Fappy. But you can forget about how the MAC interfaces the Fappy. So this is a good example of an interface that is well designed, but this communication model we have adopted in every layer. So with F1, we also do the same. So let me go back to, so with F1, we also do the same. The PDCP instance doesn't know that he's talking to F1. He's talking to an adaptation layer that at runtime, we will decide if we connect that layer with F1 or we connect that layer directly with RLC. Okay, so this is the design pattern that we follow throughout the code. And it allows, for instance, in the case of Fappy, to have a fast path when we are using both our Phi and Mac. So when you're using a third-party Phi through the Fappy interface, the way it works is that our Mac, in this case we are vendor A, our Mac will generate struct of values, our own struct, let's say. The Fappy translator will translate that into Fappy messages, and the Fappy message serialization will transmit that through whatever physical interface we have between the Mac and the Phi. Sometimes you have in your embedded board, I don't know, shared memory, serial interface, whatever. What happens when we are running the Phi and the Mac in the same machine, like we do here? We just cut at this point. We do what we call a fast path, and Mac, from that struct that it was generating, this Mac to Fappy adapter just essentially copies. It converts the struct into the struct that the Phi understands. So this, when you go through the code, can be sometimes a little bit, okay, why there are so many steps in when I'm following this variable? But the idea is to allow these clean separations. That from the point of view of the Mac, the implementation is the same if it runs in a server with our own Phi, or if it runs in an embedded small cell with a third-party Phi using inline acceleration. And last slide on Fappy. Also very important if you want to inspect what on every slot, for instance, what the scheduler is instructing the Phi to generate, and I don't know, do changes on it. The Fappy is the interface that you want to look at. It's very useful to get familiar with the spec and to the kind of messages. The most important message is probably the slot indication. The Phi on every slot boundary sends a signal to the Mac that says, hey, this is a new slot, new slot, new slot. And the L2 has to reply with everything that the Phi needs to transmit or receive on that slot. And this is accomplished via a set of messages that the Fappy spec clearly defines. And we have abstracted those in structs that are easy to manage. The downing TTI message, for instance, is what generates the PDCCH grants for both uplink and downlink. It also configures the SSV, configures things like the demulation reference signals, the CSI. So notice that from the point of view of the Phi is completely stateless and is completely dumb, if you want. Every slot, it receives all the instructions that everything that needs to compute. You could be messing here and tell the Phi to generate a DMRS scrambled with an RNTI different than the PDSH that goes with it. You are free to do that. So if you want to experiment with these kind of things. The uplink TTI messages, in a similar way, tell the Phi what things it should receive on the control channel or on the PUSCH, for instance, or if it should expect sounding reference signals. So again, if you are experimenting with uplink MIMO estimation, maybe you are interested in this. If you want to experiment what happens with extra custom parameters out of the spec, you would include those in this message and then tell the Phi to use them to receive. The Phi also uses the same messages to indicate channel quality indications, to indicate the scheduling requests. Again, very important if your area of expertise or customization is in scheduler or in the Phi, this is critical to understand. In the radio interface, we also follow the same the same abstraction model. From the point of view of the upper PHY, it doesn't know if the radio interface is an RU or is a split 8 using user P. For the upper PHY, all it does is request a resource grid from a pool, write the data there, and then deliver the resource grids to a gateway. The gateway then, depending on the implementation of that gateway, will deliver those resource grids to the lower PHY, and then the lower PHY will generate the samples that go to the user P, or will deliver that to the open front hall library that will deliver that to the RU. But again, the idea here is that we use all these gateways and adapters to break the different steps. Going then now to threading, the first important thing of the way that we have implemented threads is to differentiate between the control plane and the user plane. In the control plane, we use coroutines to run procedures. And the reason is that we find it easier for the user to understand the code, to understand what is happening. Because what you find many times is that there are many procedures, like the creation of a UI or the reconfiguration of a UI or the removal of the UI, that cannot be completed in one single function. Because maybe the CU/CP has to tell the DU, remove this and wait for the acknowledgement. And then if that fails, do something else. So there are two ways of doing that. One is send that message and then implement the handler of the receive, but then it can complicate the code and the following the state. And the other one, which is what we use, is to use coroutines. And with coroutines, essentially, you have the entire function, so the entire procedure in a single function. At some points, at points that you indicate, the context can switch. And if you are sending a message, maybe something else will run in between. But the beauty of it is that from the point of view of the reader of the code, you see all the procedure in a single function, and all the failing parts you see how are handled. The threading, same as in the interfaces, is a critical part of the software architecture. The main objectives here, going back to the beginning, are supporting small or large computers, supporting inline versus look-aside or collocated versus disaggregated. The way that, so the design pattern that we have adopted is the executor model, where we, again, decouple, it's the same idea as always. We decouple the business domain from the implementation. On the business domain, what we have are abstract tasks that want to perform some task, no? Components that want to run some task. And on the implementation side, we have threads that we can have a thread pool or we can have a single thread. The executors is what in some way maps those tasks into the actual implementation. So we can have two tasks that are mapped or assigned to the same executor, and this executor uses a thread pool to run all the tasks. We can have another model in which we have two components that push tasks to different executors that can be implemented using two threads or one single thread. So all these different execution models are created at runtime. So if you go to this file, for instance, is where we, at the start of the application, it creates the different execution models. From the point of view of the implementation of the task, the execution model does not affect it. So what does it mean? That if we are implementing the LDPC decoder, we cannot call pthreads to create threads. We cannot call to create threads or to destroy them. We need to use always this abstraction layer to create executors, because this is what will allow us to first, based on a configuration file that we will see later, or based on if it's CUDU or if it's collocated, use a different threading model. For instance, if it's collocated, obviously, there are threads that can run tasks in the CU and in the DU. If it's distributed, obviously not. So this is all, this file, for instance, you will find it in the apps folder. You won't find it in the lib folder. In the lib folder, you won't see anything that relates to threads or anything that relates to platform-specific feature. The current model that so I say current model because these models have evolved a lot in the last year and might continue evolving. But the current model that we have is that we divide the threading model in the DU-CU and the PHY and the OFH. In the DU-CU, there are three main threads. One that it's called G0B control. That these are the threads names that you see when you run htop, for instance. We'll see that later. The G0B control deals with the CUCP and the configuration of the UIs in the DU. Typically, this thread loads at low priority. It's not very time critical. The G0B UI deals with the traffic, essentially the user plane that goes between goes to the CUP and the DU. And the DU cell, this is a very important thread because it runs the time-sensitive, the critical path on the L2. So that's essentially the thread that runs the scheduler decision when a slot indication arrives. So we saw before in this Fappy diagram that the PHY sends the slot indication. Then the scheduler has some time, it's one slot actually, to generate these two messages. So this task runs in this thread because this is a very critical task, needs to run in high priority. This is a class diagram of the DU in particular. In the website, we just published last week a developer's guide, and we also added class diagrams for all the CU also. But essentially on the DU, you have the traffic that, the uplink traffic, and that you have the MAC uplink processor. This the multiplexes the traffic in the RLC uplink bearers. This goes to the F1 bearers and then goes to the CUP. And in the downlink, you have the same that goes to the MAC downlink processor. The scheduler receives the messages from the HIRQ bits, the UCI, the CQI bits, the scheduling request indications, and generates scheduling results. And you have another class that is the PRAC handler. And then you have what we call the DU manager that includes a UE manager, a cell manager, and the SCTP manager. The critical path I was describing before is this, in L2 is essentially the time from the slot indicator to the, so there are two steps that this task, this thread runs. The first one is the scheduler decision. So, oops, sorry. It decides, essentially generates the downlink TTI and uplink TTI messages. It decides what will be scheduled in the downlink and what will be received in the uplink. And then for all the downlink PDUs, it calls RLC to generate the RLC PDU. This task, so this first part is easy, and usually it's very quick. This second part can become complex, especially if there are many retransmissions in RLC, because the RLC needs to go through all the transmit window, and when there are many users, this can create lates. On the L1, we have what we call processors. We have the downing processor. This is the case of the downing, that creates tasks for the, well, no, not creates tasks, calls the PDCCA processor, the PDSCH processor, and the SSB processor, and each of these will create tasks. In most cases, the tasks are simple and small, like generate the PDCCH grant, the entire message, or generate the SSB signal. But in the case of the PDSCH, since a single transport block can be a very long task, it is further divided into code blocks. Each code block task encodes a code block and modulates the code block, and applies a scrambling to the code block, and then maps it directly into the resource grid. This is done to achieve parallelism. And this is how the threading or the parallelism model works in the PHY. We have the Fappy adapter receives at this point this is the L2 generates at this point the scheduling decisions. As soon as the scheduling decisions are transmitted to the PHY can start generating the PDCCH, but it cannot encode the PDSCH until the transmit data request arrive. When the transmit data request arrive, in this example, let's say that there are 2 users, and it needs to generate 2 transport blocks, 1 for each user. This transport block will be further divided into these tasks, 1 for each. Let's say that there are 8 code blocks. An extra task is the DMRS that is generated in a separate task, let's say. And this is executed in a pipeline fashion. So on this slot, you will start generating. So this thread or this task will generate this subtask in the next slot. Before the previous one has finished, we're already generating tasks for the next one. Everything in the end is processed like on a pipeline fashion. The pipeline length, we call it max proc delay in the config file, and it's a parameter that you can configure. And that determines how early, so this is a value that the scheduler needs to take into account to know how early it needs to send the data to the PHY. These are the names of the threads that you will see in HTOP, and we will come back to this later when we see how to optimize or how to fine-tune the threading model. On the OFH, remember the OFH is the library that, or the block that generates the CPRI messages for the O-RU. There are 4 important threads. One is the RU timing, which is a thread that is continuously monitoring a timer, the Linux timer, and then when it detects a boundary in the slot, in the symbol or in the slot, generates an indication to the upper layers. The RUTX and RURX are in charge of generating the Ethernet frames for the control and user plane. And in the case of the downing, the compression is done in 2 separate threads in parallel. So why the threading is so important? Because it determines, so essentially the execution time of these tasks will determine how often there can be lates. Lates have consequences, because if you miss a deadline, the packet won't go over the air, the user won't see it, and that increases the blur. How critical are lates? It depends on your requirements. This is the typical, this is a histogram of a task. In particular, this is the generation of the TX data message. And notice that this is log scale. So most of the times, this task completes in less than 200 microseconds, but it has several outliers. For instance, let's say that your deadline for this task is 400 microseconds. So that means that 1, 2, 3, 4 times every 1,000, you will miss the deadline. Well, 1,000, no, 10,000, whatever. Is this a lot or not? Well, you run this task 2,000 times per second because you run this task on every slot. So if every 10 seconds you are missing one deadline, is it critical for you or not? That's up to the application. In R&D or if you are doing experimentation, maybe it's not critical, and maybe it's okay if you set the boundary even here and you see 5, 10 lates per second, 5, 10 retransmissions per second. Maybe you don't care. In a commercial deployment, the boundary needs to be here, and you need to ensure that in 2 or 3 days of operation, maybe you see one missed deadline. So how important the real time is, it depends really on the application. In some cases, maybe you don't need to worry about, but in others, you need to worry about. What happens when there are real-time lates? So I insist a lot on this because this is a recurring question in the mailing list. And sometimes, not always, but sometimes is an indicator that things, so it's the reason why things are not going well and you cannot attach the phone. It all depends essentially on how severe they are. If you have 100 lates per second, then that probably you won't be able to attach the phone. So what are the consequences of, well, first of all, where are the lates and what are the consequences? The most important lates are in these 3 parts. In L2, which means that the DUCL thread was late to generate the downing TTI request, the deadline is 1 slot, and if it misses the deadline, the PHY won't generate a signal for that slot. And the UIs won't see the grant, won't transmit anything, won't receive anything. If it's a downing, for instance, the G0B will expect an acknowledgement, it won't see it, and will send a retransmission. It's similar if the case of the PHY late. In the downing, even if the PHY receives the instruction from the MAC on time, it can be late in this pipeline. It can be late in encoding the PDSCH and can exceed max proc delay. If it exceeds max proc delay, it won't arrive on time to be transmitted over the Ethernet, and there you won't see it and you won't transmit it. And in a similar way, in the OFH library, there can also be lates. And even if it arrives on time there, maybe because there is congestion on the Ethernet driver or some other reason, it might not be arrive on time to transmit that on Ethernet. Another late that sometimes users see it in the logs, but typically is not, well, I would say that it's a little bit less critical, is an HRQ late. An HRQ late means that the message arrived well to the HRQ indication arrived well to the G0B, but it didn't process in time and didn't arrive in time to the scheduler so that the scheduler can do the decision on the next slot. This is not super critical because if you have a few users, that only means that that user cannot be rescheduled again, but probably there are other users that can be scheduled. And it won't affect a lot in the blur, only if you have one user. It depends on a few things, essentially the number of HRQ processors, the TDD pattern, and the K1 and K2 values. So one of the things that we recommend is to reduce K1 and K2. You will see later that in the... Okay, so this is so far regarding the software architecture. I don't know, maybe I stop here and see if there are any questions before I move on. Or you want me to continue with CI/CD? Yeah. Yeah. Yeah, very quickly. So yeah, I was trying to show later the documentation. The documentation page is a very important starting point always. And if you go here to the developer's guide, software architecture, you will see these class diagrams that map directly to the classes in the code. Sorry? Yeah. You mean this plot? Yeah, there is one thing that we call traces. If you set this to true, there is a server that is called, so a class that is called file event tracer. If you look at the code and navigate through it, you will see that it's a tool that we use to profile parts of the code. And it has some methods to start timer and stop timer, and then it records everything into a file that then you can use, you can basically parse that file and generate these plots. Any other question?
So with CPU pinning, I mean, do you think that would lower any of the latency requirements that you have?
The question is, if we CU/CPU separation, the performance will be lower.
So say like you're using system D to set your processor, you know, I want XYZ cores on this specific task, you know, would that lower your latency as well, potentially?
On the CU/CPU, doesn't affect a lot the latency because it's the control plane. You mean the CUP, maybe?
No, just for CPU pinning. So just generally speaking.
Generally speaking, okay. Yeah, to be honest, we have experimented a lot with latency. We even added options in the configuration file to assign layers to different groups of threads, of course. But we realized after a lot of debugging that usually letting the scheduler choose the affinity is the best, unless you know very well what you're doing. Because I guess that I don't fully understand it, to be honest, but I guess that what is complex is when tasks of different scheduling scheduling priorities or models coexist. So if you pin a task, so that is using the SCED FIFO policy, for instance, for kernel priorities, and you only pin to one core that is also being shared with another that is a SCED other, for instance, I don't fully understand how that behaves when there are things like condition variables or this kind of synchronization metrics. And I have the impression that sometimes a task with lower priority is preventing a task with higher probability to run because it's holding more mutex or something like that. And after experimenting a lot and defining these configuration file options to let everyone play, we found that this operating system decisions were the best. But I will go through this configuration file later, and I invite you to play and see if you can find better solutions. Any other question on this threading or interfaces? No? Okay, so let me move on to the CI/CD. There are just a few slides here. Just wanted to highlight the way our approach to CI/CD and to branch management. This is the branch that all of you see in the repository. Internally, we have a clone of that repository, and we use these other branches. What we call our main development branch is what we call dev. We follow the typical MR based approach to develop. So if you are developing a new feature or a bug fix, you create a branch, add your commits, and then merge back. Before merging back, this needs to pass the test on the CI. It's essentially a battery of jobs that test that branch in particular. When that passes, it can be merged into dev. Every night, we run what we call the nightlies, that are, again, a set of even more extensive tests that run automatically they start at 12, for instance, and run all night. If that nightly fails, for instance, a developer will clone that branch, create the fix, and merge it back. Once the nightly passes all tests, then it can be merged into what we call the next. Next will be the next main branch. Then on a weekly basis, we do even more extensive tests that take longer to run than one night. And basically we run them over the weekend. And then on Monday, we know if the code from last Friday was good to be released or not. This is what has allowed us this last year to generate more frequent releases. In total, we have more than 4,000 unit tests and 140 end-to-end tests. I discussed with some of you individually that over the last 2 years, we transitioned from, at the beginning, we were trying to create many end-to-end tests to test mobility, to test all combinations of MIMO, all combinations of different bandwidths. But we realized that that wasn't the approach, because the more end-to-end tests you have and the more complex they are, the more likely is that something fails. And it's a user P, it's the phone, it's a power cut, anything can happen. But then the test can run well, and you don't know if it's failing the application or the test. So we decided to simplify a lot and focus and rely more on unit test and integration test. In terms of the end-to-end tests, we have this kind of infrastructure in our labs. We have racks with user Ps. We have a shield box where we have a couple of phones that we control with a PC using the ADB interface. And we also use ZeroMQ with a Malisoft UI. Many of you are using ZeroMQ with SRS UI, but it is also possible, and I think that we even open sourced the tool to do it, to use the Amaris of UI. They give you an API to implement your own RF frontend or driver to your RF frontend. We use that to implement a driver to our Xenon queue, and then we are able to connect the Amaris of UI with our G0B. That is very, very useful because it's a more controlled environment than using RF. And we actually run that even on PR jobs. We can run an end-to-end G0B with the UI and perform basic attach. In terms of hardware, up until now, we have been relying a lot on user piece. Now we are starting to integrate O-RUs in the CI/CD, but it's complex to automate it. And the next step, as I was saying yesterday, is probably to start using more the Viavi RU emulation. In terms of operating systems or distros, we built on all these and combinations of these using different compiler versions. Sorry. And we also use a lot other sanitizer, thread sanitizer and Valgrind. So one of the advantages of using XeronQ is that it can run in non-real time. So it can run in very slow machines, or you can run it through Valgrind. And then we can run end-to-end our G0B doing an attach, an iPerf, and multiple users with Valgrind or other sanitizer, which guarantees or is very helpful in finding memory issues. Another tool that we use in our CI/CD is Retina, which is our own orchestration framework that, as everyone, we have also developed our own. That essentially allows us to, it's container based, allows us to deploy, for instance, the code GUI with what we call the Retina agent in one node, and in another node, for instance, we can run the G0B and the 5G core, and we orchestrate the deployment with this framework. So how to get started with the G0B and an O-RU and a code GUI. I know that many of you work with srsRAN and work with user piece, probably most of you. But I'd like you, if you have the opportunity, I'd like to convince you or to push you to start using more these front ends and code GUIs. In this is the setup that I took yesterday, this picture that we will run today. In this server, we will run the core network and the G0B. Everything in the same, let's say, collocated in the same machine. And here we have this, the Foxconn RU. We have here in the ground the PTP Grandmaster from Pulsar. And as you know, in O-RAN, the plane is separated from the control and user plane. So this guy is connected to both this and this to drive the timing. Thank you. Setting up the timing, to be honest, is the most difficult task in setting up any PTP, any O-RAN deployment. As you can see right now, because it's not working. I strongly recommend to look at this guide. Here, I won't go through all the steps on setting up PTP because it's not that it's difficult, but it's long. But Brendan in our team did a very good job in putting together this guide. It explains how to, in this example, it uses the Venetel RU and the Falcon switch. The Falcon switch, I mean, it's more expensive than the Grandmaster, and in some, not always you would need it, but it's very useful because it allows to connect from a single server, control different RUs. We use it for backplane, and so for front haul and back haul. And in the future, we can use it for mid haul also. And in this guide, it explains you how to configure the NICs, how to configure the PTP in the Linux, how to set up the Falcon. For the RU, you need to check the manual, and essentially all the steps to get it running. Yeah, so then, as I was saying before, always when if in doubt, always go to the documentation. And I would like to highlight these guides. The code GUI knowledge base, I will go on to it later. And these two tutorials, I find them the basic and the very good starting point. This one describes how to connect, how to attach a code GUI with the G0B, is essentially what I will do today. And this one is how to set up the O-RU. So to install srsRAN, there are two ways. This one, I don't recommend it because it's essentially installing the binary packages, but all of you here are developers, so you want to look at this way of doing. The pro way, it's very easy. Clone the repository and use CMake and make to compile it, and then you're ready to run it. Before running, always don't remember to run this script that essentially sets the CPU clock to maximum and does a couple more things, but always don't forget to run it. You only need to run it once when you start the machine, not every time that you run the G0B. And then you're ready to run the G0B. It's this simple command. In this version, well, since we started this new version of the G0B, we moved to YAML configuration files. YAML is really powerful. You will see now how you can combine different configuration files to concatenate parameters and how powerful it is. One thing that is important is that not all values need to be configured. So it's actually possible to run the G0B with no configuration file, with no parameters. And what it will do is just use a set of parameters that does something. Now, you won't know which frequencies, which PCI, anything will take default values. But it's important that you are aware that there are many configuration parameters. I will go through them now. But if you don't set them, it will take the default. The default typically is something that we have tested well. So in case of doubt, just comment it and let use the default. Yeah. I will show it's in the next slide. Yeah. Yeah, you will see now. Yeah. So how to pass the configuration file? Easy with -C. And then notice how you can concatenate multiple configuration files. So you can have one configuration file, for instance, which is the base config, and you set the AMF, you set the SDR driver, and you set the basic cell configuration, and then have, for instance, two configurations for different frequencies, one for N7 and one for N78. Then you can run, just concatenate the two configuration files, and the second will override the parameters of the first one. So for instance, you can concatenate all the files that you want, and you can have profiles for MIMO, profiles for slicing, and then just, if you want to run MIMO this time, you pass MIMO. If not, you don't pass it and you say so. This is very powerful. Another useful command is the help, which tells you the default values. If you do -H, it will tell you all the sections in the configuration file. And if you, for instance, do -H and AMF, it will tell you the different options in this section and the configuration files. So it tells you if it's a text value or number, the range that you can do it, and the default value. And again, I will go back to the documentation, because in the documentation, you have this full list of all the configuration files, of all the configuration parameters. And actually here you also have the defaults. So you can see that there are many, many, many sections. And remember, if you don't set them, it just chooses the default one. And by the way, also here, you have a short documentation of what this value corresponds to. And you find the same if you just type -h. This text is the same that you will see there. The CODE, the SIM configuration, is a very critical step. So whereas in 4G and with srsRT, it was fairly easy to configure the network, and any phone that you would pick and just switch off power airplane mode and would attach. Now in 5G, it's not so easy, and it depends a lot on the phone. The problem is that when 5G started, many of the phones that were advertised as 5G were only NSA. And then you started to see some that were SA, but it was not the default mode. They always try to attach to 4G. And sometimes, even if you have them in a shield box, and it only sees a 5G network, it won't attach, and it will continue and continue and continue to try to find 3G, 2G, or 4G cells. It seems that they only go to 5G if a 4G network tells them to do a vertical handover. Otherwise, they won't do that by themselves. That depends a lot on the phone manufacturer. And sometimes we have also seen that depending on the combination of the SIM card and the phone, it can also give troubles. So a few recommendations. I guess that the first one is don't use a phone that you have bought from Verizon or AT&T, because it will likely be locked to those frequencies or PLMNs. The second recommendation is, again, use our documentation to look at the list of phones that we have tested. So in this page here, you have two tables. One is the list of countries that we have tested, and this other is the list of people like you have reported that are working. And for instance, you have tricks. So in the notes column, you will see things that you can do to, in case it doesn't work, to try to make it work. But it's important to use a test SIM or a programmable SIM card. Important to match the MCC and MNC with the network. And this also is, we find it very useful, is to disable the SUPI concealment. The second step is to make sure that you add the same credentials into the 5G Core subscriber list. If you are using Open5GS, you can use the interface to enter the keys. Again, everything is explained in the docs, and I recommend to follow that. The SIM slot, this is also very funny. Many 5G phones have two slots. We have found that sometimes it would attach if you put the SIM card in slot 1, but not in slot 2. So again, that's something that you can try. If you see that it is not attaching, try switching the slot. Sometimes also we find this necessary is to force an R in the service menu. You dial this as if you were doing a call, and it will show up a menu in Android. And then you will see that there is an option to select what RAT you want to connect. And it's better if you choose NR only. If you choose NR LT, it will always prefer LT and sometimes won't see the NR one. Then also make sure that the APN is correct. Otherwise, the phone, you might see attached, but you won't have traffic. Then, for instance, another thing that was funny that happened with the Pixel 6 that is documented here is that the Pixel 6 requires going to this hidden menu and disable these two parameters, because what happened is that it could attach, you started doing traffic, and after 2 minutes, it tried to establish the IMS session. If it can't, it just disconnects. So if you are seeing strange things with the code GUIs, go to this list and it hopefully will be helpful. If you want, you're setting a network and you want to have internet access from the phones, it's also mandatory to run these two commands to forward, so the phones will connect to this guy. You need to configure this guy to enable IP forwarding to the outside world. Then recap of what you obviously need to run the GNOT-B is a core network and a radio frontend. The radio frontend can be SDR or an RU. So what happens when this is what happens when you run GNOT-B and there is no core network. This is the error that you will see. Or if the configuration of the IP is not correct, you will see fail to create a CTP gateway. It cannot connect to the core. Or if you don't specify an SDR frontend, or it can't find, you specify it, but it can't find it, you will find this error, unable to create the radio session. So, yeah, so then you need to make sure that to connect the GNOT-B with the core, in this case is the Open5GS, the AMF address here matches the UPF and NGIP addresses, and the bind address, this is the address that the GNOT-B will create to receive packets from the core. No, this one, yeah, you don't need to specify it in the core. A question that many people ask is what happens with N2 and N3 separation. In the srsLT, you could separate them. In this version, not yet, but it's a small feature. Hopefully, we will add it soon. But at the moment, N2 and N3 need to go on the same port and need to be on the same subnet. When you're using an SDR, obviously the user P must be reachable. If you are using a V210, please don't connect it on a USB 2 port. Make sure of that, and don't use USB hubs unless it's a USB hub that you have tested and know that it's very high performant. The external clock, that's something that is also highly recommended. Some people said, oh, but before it was working without and now it doesn't work. It doesn't depend on the GNOT-B. So the job of synchronizing is on the UI. You might find some UIs that are able to synchronize even if you're not using an external clock, and others that can't. And also from radio to radio, the clocks change a lot. So the clocks have, in the user P, for instance, an uncertainty of 3 kilohertz. It can go in one direction. So that doesn't mean that it's always the error 3. It can be from 0 to 3. So you can be lucky and your user P has a good clock, or you can be unlucky and it doesn't. In any case, we always recommend to use an external clock or a GPSDO. So this is the configuration that you need to enter when you're using an SDR frontend. And if you are using O-RU, the section is RU OFH, and it has all these parameters. From all these parameters, so correct me if I'm wrong, Borja, but these ones are provided by the RU vendor, right?
Between the RU vendor
and your network setup. But to understand this, probably we would recommend to go to the O-RAN specs. These are basically time intervals or time intervals that are defined in the O-RAN specification. This set of values configure the compression for uplink, for downlink, and PRAC. Obviously, the RU needs to have the same configuration. I don't know how many different compressions we support. I think that 9 and 16 are supported. The IQ scaling is quite important. The best starting point is 1.0, which will try to scale the IQ samples to a value that makes sense. But depending on the RU, it can be low or it can be too high. The best at this point would be that you generate the signal and you look with a spectrum analyzer, or even better if you have a Rode and sparse demodulator that can tell you the things like the EVM, because then you can fine tune this. If this is too high, it will create distortion at the PA. If it's too low, maybe you are not using the entire dynamic range and the signal will be very weak. The best to calibrate this is to have proper equipment. Here you need to configure the network interface name at the DU side. And these are the MAC addresses for the RU and the DU. The VLAN tag that you need to check with the RU. And these are the EAXC port values that, again, you need to check with the RU. And then you're ready to run. Just the command, the GNOB binary, and the configuration file. Before it's running, or actually this you can do once it's running, especially when you're running with an O-RU. So here I will go through a little bit of a checklist. Most important is check the timing. Check the PTP at both the DU side and the O-RU side. This is what the command to get this information depends on how you have installed PTP, but typically this is written into a log file. What you want to see here is what Borja values below 100, I think, no?
Ideally below.
Or ideally below 20. The RMS. You want to look at the RMS and make sure that the value is below 20. If the value is very, very high or it's oscillating between a high and low value, means that something is not good at PTP side. And this will mean that you will lose packets, or that the synchronization will not be good. Second checklist, obviously check in the console output that you see something like this, that it's generating the signal on the bandwidth and the frequency that you want, and this is what you should see. No errors, no messages. Then you can check that on the O-RU, it's receiving the data in the control and user plane with no errors, and it's receiving it on time. This log, for instance, is from the Foxconn RU. You want to see that the control plane on time messages, in this case, increase, and there are no lates, there are no errors. In this case, this error total, forget, because it's actually correct packets, no? But it's user plane packets, it's just a misleading log line. Second thing that I would test before jumping into attaching the UE, look at the spectrum analyzer and verify that you are actually transmitting something. One last thing that to have a good deployment, everyone should go through, but typically nobody does, is to calibrate the TX and RX powers. So the way open loop power control works in NR is that the G0B broadcasts on SIB the SSB block power. The UE measures the power that it receives, and based on what we say that we transmit, calculates the path loss. Then the G0B also tells the UE what power it should aim at for all the transmit signals, for the PREC, for the PUSCH, and for the PUCCH. These are the powers that we want to receive the signal in dBms. So if we say that we want to receive the PREC with 100 and the path loss is 60, so the UE will transmit that at -40. And this is important because if we say that we are transmitting -16, but in reality we are transmitting 40, and the UE is at some distance, the UE will think that it's very, very, very close and will transmit tiny power, and we won't see it. Or on the other way around, the UE might be transmitting full blast power and it will saturate our receiver because it will be very close, and the quality of the signal will be very bad. Or also it can happen that the UE thinks that is so far and we are requesting a target power that is so high that it exceeds its power capabilities and it won't even try to PREC. Okay, so this is sometimes, not always, but sometimes is a cause of problems. So once we have verified all this, we have looked at any question here so far? We have looked at the spectrum. It's time to turn airplane mode off and wait for the PREC. One trick with airplane mode that I would recommend is that when you're doing experiments, always first start the G0B and then turn off airplane mode. The UE should attach, and when you finish your experiment, before closing the G0B, turn on airplane mode again. Why? Because if you first turn off the G0B and the UE loses the signal, it will try to resynchronize again, and it might blacklist that channel because it might say, okay, this signal suddenly disappeared. I have been looking here for 1 minute. I don't see a signal. Next time I want to look here and I will look somewhere else. So it's always better that you make the UE think that the signal is always there. So next time when you turn off airplane mode, the first channel that it will go to look will be this one, and it will attach very quickly. So are we, is the demo ready? Are we ready to, or it's fine, we can go without it. So it's not critical. So when you start running the G0B, this is the console that you see. All of you are probably familiar with it. I will just go through the different parameters. We have here the CQI that is reported by the UE, the rank indicator. This is the MCS that we are using for the downlink, the bit rate, the number of ACs, positive ACs, and the number of negative ACs. This is the blur. This is the downlink buffer state. So if you see it to 0, means that in this case, for instance, if this is 0, means that the bit rate is very low, but we have nothing to transmit. Or as soon as some data arrives to the buffers, it's transmitted immediately. This is why you see this to 0. In a similar way, you have the same for the uplink. You have the uplink SNR, the uplink MCS, the uplink bit rate, the number of OKs, and the number of KOs. And this is the buffer status report indicated by the UE. So in this case, the UE is saying that it has full buffer, and we are allocating all this traffic. Logs are very useful, and there is a section in the configuration file where you can choose what layers you want to enable log. You have different log levels like info, debug, warning on or error, and it's useful to understand where the error is happening, or if, for instance, if you have a PRAC at all or not. There is, again, in the docs, this one I don't remember what it is, but in some point in the docs, yeah, here it explains the different fields of the log level of the log lines. But for instance, this is a PDSCH log where you have the RNTI, the HRQ process, the K1 value, the PRVs, the number of the symbols that was allocated, modulation, transfer block size, and this is the execution time for the generation of that message. And also pickups are very powerful. You have pickups at different layers, NG-up, E1, F1, MAC, E2, and GTPU. You can enable or disable them. And so let's go to the kind of yeah. Yeah.
File name you can point.
So the traces you need to enable this, set this to some path to a file line, and then you also need to enable this Boolean in the code. This one is defined at compile time because otherwise it adds a lot of overhead. So what to do when things go wrong? The first problem that you can see is that you don't see anything in the logs, in the console, sorry. You see this. So you turn off airplane mode, but you see this. You don't see any line like this one. Even you look at the logs, you enable the logs, and you don't see any PRAC. So the phone is not, it's either not attending to PRAC or it's sending the PRAC and you're not seeing it. Things that you can check, that you would check here is the SIM configuration, the SIM tray, the MCC and MNC levels. Check that the signal is there using the spectrum analyzer, and check the power levels. Say that you see the PRAC, for instance, you see a log like this. This actually comes from a user in the mailing list. You see the PRAC, but then the SNR is negative and nothing else happens. If you see an SNR like this, minus 19 or minus 15 or minus 10, this means that there is really no signal. And the reason that there is no signal can be multiple, but can be that the UE, so we sent the grant, but the UE didn't receive it, and then it's not transmitting, or that the UE is transmitting at so low power that it's not even being received. Typically, what would happen with message 3 is that in the PRAC procedure, the UE chooses a preamble, sends it, and we send a random access response for that preamble. Sometimes, if the synchronization is not correct, the preamble that we detect can be wrong. And if the UE sends a preamble for the preamble number 2, and we detect, in this case, the 1, we will send the random access response for preamble 1, and we won't see any signal because the UE didn't receive the random access response. So in this case, what you could do is look at the timing advance of the PRAC, look at the SNR levels, make sure that you actually detected that PRAC, that it wasn't a false alarm, for instance. The UE does not attach, but you see something in the console. So in this console trace, you see some lines, but you don't see really traffic. You see just a few kilobytes, but in the phone, you don't see the 5G signal, for instance, it has not attached. This, what can happen is that it, or most likely happens, is that it succeeds in the random access response. So as soon as you see an entry of a user in this console means that the random access response was correct. It received the connection setup, but it didn't complete the authentication with the network. Then what I would recommend is to go to the 5G core logs and see there what happened. In this case, for instance, a typical failure or a typical error is that we didn't register correctly the SIM card in the 5G core, for instance. You would see something like authentication reject. Say that the UE attaches and you can do ping, but throughput is very low. What I would do here is first check the DLBS to make sure that if we are pushing a perf, this a perf is going to the stack, that you got the IP correct, all the routing in the system is correct. If you see, like in this case, okay, I'm seeing a high downlink BS, that means that the traffic is arriving to the scheduler. But why my bit rate is so low? Check the blur. In this case, yes, the blur is a bit high, so there is some problem there with the blur. Check the MCS and the SIGY here. Here, what this is telling me that the UE is seeing a good channel. The UE is reporting a SIGY of 15, and we are choosing an MCS that correctly corresponds to the SIGY. So what happens? Why the blur is so high? One potential problem here could be that the uplink is not correct. Remember that the UE sends the acknowledgements on the uplink. So the UE could be decoding everything correct and could be saying, yes, I'm receiving everything correct. But if we don't see these positive acknowledgements, we will retransmit. Here, the uplink signal is not bad. So what can happen here, the most likely is problem are real-time faults.